Hello everyone, this is going to be the first of two of your adaptive design labs for this week, particularly for Thursday, May 26th. What we're going to start out with is a basic box structure like we've been working on in our class so far. It just looks like this. It's a simple box. Make it 30 feet wide by 20 feet tall with a 1 foot thick outer surface edge thickness, and then just set the glass back 5 or 10 feet. In fact, 10 feet is probably more accurate, just in terms of having some clearance to see things. What you have here is just a single layer of glass to simulate the idea of a sort of balcony or porch condition. Okay, this is a simulation. It's not meant to be an actual architectural condition. We're just going to start with something that looks like this. Once you have this, go ahead and get Grasshopper open. Okay, once Grasshopper is open, we're going to have to go through the process of setting up the model for modeling. So what exactly are we doing? I mentioned that this is going to be an adaptive design lab. So basically what I'm going to provide for you is a walkthrough of a simple exercise. And that's, in this case, it's a handrail and a guardrail. And when I release you, and this will be the first half an hour of class, when I release you for the next hour, then you're going to have to go through the process of adapting to a new model, which I'll introduce at the end of this video. So the walkthrough will take us through setting up a guardrail with a reparametrized glass panel in the center, and then we will pipe the actual structure of the rail itself. So to get us started, what we're going to do is actually start to reference in the geometry itself. So what I'm choosing to do, since this is going to be a guardrail that kind of sits at the lower 4 to 5 feet of the opening, well, actually, it's not 4 to 5 feet, it's 42 inches. But it'll be at the lower 42 inches of the opening. And so I'm going to place a curve along the edge that I can reference in order to model off of. So I'll go here to curve. And I'll have to actually model one in. So let me go to line, and I'll draw a line from here to here. You probably won't see it there at first, but set one curve and set it to this curve right here. So now that we have our curve referenced in, we need to think about how we're going to actually construct it. So usually a handrail or a guardrail kind of sits a few inches above the ground itself. So what I'm going to do is move this thing upwards a value of, say, 6 inches in order to give it a slight gap at the bottom. Okay, and it won't necessarily be grounded. In fact, the posts right now at this point are going to be floating, but that's okay. It's just an abstract exercise for right now. So to move it up, the good thing about moving in the upwards direction is that up will pretty much always be up, unless we're going to change something here. But basically, I'm going to do under transform and Euclidean, I'm going to go to move. And it's going to ask for the geometry, which is going to be the curve. And you'll see that it kind of jumps upward a value of 10 right now. This is 10 feet. My file is set to feet. Then I can just make sure that I calibrate how far it's going to go. So since this is already defaulting to the z-axis, all I really have to do is give it a numerical value. So if I go to a slider and I say 0 to, let's just make it 48 inches. Because I went with inches, I'm going to have to put in a mathematical operator. So under math operators, I can do a division, which with a static number 12 using a panel will give me a slider in inches, even though my measurement is going to be in feet. So right now 0 is not doing anything. Oh, you know what? I think I do need to give it a unit z. Yeah, that's correct. I do. I need to give it a unit z because Yeah, number to vector. Got it. Sorry, my mistake. So we do have to go to vector and add in unit z. And I'll just plug this in here, plug this into t. And now, as I slide my slider back and forth, you'll see that it's going up to a value of 48 inches and then back down to whatever I set it to. So to start off, my first extrusion is going to be 6 inches. That's right there. Next up, I have to extrude, or sorry, not extrude, I need to move another one of these. So the cool thing about the vector option of moving something is that if I just plug in a second numerical value, like maybe I put a 6 and say a 42, which is going to be the top rail height of our railing, then as long as there are 2 inputs here, then this list will expand from 1 item to 2 items. So I can copy the slider down and then make it a 42 and plug that in holding shift. And now you see that there are 2 input values. Also, the wire has changed to show me that there are 2 values going through. And you can also see it over here. So when I hold the move command here, if I slide back and forth, you see my second vector, or sorry, my second rail is now movable. So I've got one at 6 inches, I've got one at 42 inches, and I need to start progressing into actually developing the subdivisions for the panels, really. And there are a number of ways of doing this. In fact, what I am going to do is kind of pull it off the edges slightly. And so I'm going to reparametrize only on one direction the edge of this rail so that it doesn't hit the side. So I'll have to make a surface first, then reparametrize it. And that's going to look like this. I'm going to go to surface and freeform. And remember, I mentioned that loft and ruled surface have 2 different ways of operating. Loft will take 2 curves that are in 1 list, and ruled surface will take 2 curves that are in 2 lists. So if I go to loft, since I only have 1 list output with 2 curves, I can plug that in and it'll create a surface. Now from that, I have to reparametrize just the width, not the height. I want to make sure the height stays where it is, so that would be a 0 to 1 value. But the loft here, now I'm going to go to math and domain, and remember, we use construct domain squared in order to reconstruct a newly reparametrized subdivision of a surface. And that would be under surface and utility and isotrim. I know it's weird. It says subdivision, but it's not really a subdivision because it's only going to be 1 new surface. But anyway, we can plug the surface into subsurface, and then we plug the domain into domain. And right now you see it's going down to the bottom there, and our values here are 0 to 1 and 0 to 1. We have to right-click on S and reparametrize, and you'll see that that new value is 100% of the original surface. So taking a step back then, if we override the connections into this, then we can reduce the value. And so in this case, if my height is going to stay at 100%, I only need to figure out, is it the U or is it the V that I need to reduce in order to reduce the width a little bit. So I can do one slider at, actually, let's just do it this way. Let's go to static numbers. We'll make one at, say, 0.05, and I'll plug that in. In fact, that's going to be way too far of an offset, so I'll make it 0.01. There you go, that's a little better. Copy that down, and I'll make this one 0.99. Okay, sounds good. Oh, also, if you wanted to make it really fully parametric and you wanted it to absolutely be even on both sides no matter what, you could get rid of this and use 0.01, but then for the other one, you start at a value of 1. and then you subtract the 0.01, and you put it in under math, operators, and subtraction. So you say 1 subtracted 0.01, you put it here. So that way if I change this even to 0.05 again, then it's going to reduce both sides. But I'll leave it at 0.01. So this is our new iso-trimmed surface. And now we are tasked with actually creating panels. And so I'm basically going to subdivide this again into individual panels that are, approximately 4 feet wide. Doesn't have to be exactly. And then I'm going to take the center panels of glass and I'm going to reduce their size. However, I want to do one further modification first. Because this element is kind of sitting in plane with the actual front face of the building here, I'm going to move it backwards. I'm going to move it backwards into the space, and then for a little bit of an artistic effect, I'm going to kind of tilt the glazing forward to give you a little bit of a tilting action to it. And so I'm going to select this curve and just kind of push it in 1 foot so that it sits a little bit back. And then I need to add a rotator. And we had a number of discussions about the different kinds of rotations we're going to do, or we can do rather. And so I'm going to take this surface that I just created and I'm going to tilt it outwards before I do my subdivision. The truth is, you could really do the tilt part later. However, once you actually subdivide the geometry, then you have multiple geometrical lists that you have to tilt out. So you'll have the individual panels, you'll have the edges, you'll have the pipes that you create around them. But now, since we just have one surface, it's smarter to do it here. So under the Transform tab and Euclidean, we have 4 readily available rotational options. We are able to rotate an object around an axis, which in this case is going to ask for a line. You can see that icon means that it's a line. Also, it's preloaded with a line at 10 feet. Also, we have available to us Rotate 3D, and this Rotate 3D has a base geometry, it has an angle, and it has a center of rotation, and it also has an axis, but this axis is going to be a vector. So that's an important distinction. Outside of that, you can do it based on a plane, or you can do it based on, well, they're both rotate and plane, but they're both axial related. So in this case, we have a line, and if I just want to tilt it outwards, I could actually rotate it around its base line right here. So I'll go use this one here, rotate axis with a line, and plug the surface in. And you see that it defaults to a value of 90 degrees or 0.5 pi. And the rotation axis is preloaded to the bottom of its own definition. And so what I'm going to do here is override the connection to the line with the original line that I created right here. It's the curve. So I'll connect this to that, and you see it kind of slides in a little bit. So that is the same as that. That's good. And then I just need to change my rotational value. Now, I'm not going to want it to tilt very far. I only want it to tilt just barely outside of its original position, but not quite as far as the front face of the building. So it might be 2-3 degrees. So I'll just make a slider from 0. I'll start at 2.55 to a value of 5 degrees maximum, probably. And remember that the angle is going to ask for radians. So under math and trig, you're going to convert that numerical value from degrees to radians and then plug that in. Oh, whoops, I connected it to the wrong spot. Sorry. Plug it into A. There you go. And what you're going to see here is that now I can go from my original spot all the way out to 5 degrees. Oh, wow. Okay, so that's a lot smaller than I thought it would be. So we can change our maximum value to 15 degrees. and then we can kind of tilt it out a little bit more. Now the truth is it's not really going to tilt very much because we're going to have a handrail in there too, probably. But this looks like probably enough for me right now. And at this point, I kind of have a lot of geometry here, old stuff that I don't really want to see. So for now, I'm going to turn off everything except for the final surface that I generate right here. So now we have a couple of steps left. We are going to subdivide the panel and then reparametrize each of the individual subdivided panels to make them a little bit smaller by a smaller percentage. And then we're going to put pipes on the rails. And so you'll see kind of the finished product here. So what I'll do here real fast is just go to the subdivision. So if we go to math and domain and divide domain squared. And remember, divide domain squared kind of comes paired up, at least in most of the assemblies we do in this class, with isotrim. Isotrim is the one that's under surface, it's under utility. We've already used it before in this definition. It's right here, subsurface isotrim. And remember, these form a triangle. So the surface output gets plugged into the I input for base domain. That domain, once it's subdivided by our numerical sliders, which we'll put in a second, gets plugged into the domain input of subdivide surface. And then the base domain surface gets plugged into subsurface. And this is what you see here. This is the preloaded numerical values of 10 subdivisions in every direction. The next step for us here is to just change the amount of subdivisions, because I only want vertical subdivisions because I'm going to put a singular glass panel in each one of these. So I'll make sliders from 0 to 10 and plug them into U and V. We'll start off with 1 in the U direction and then, okay, good. So that's actually the proper place that I want it. And it looks like 6 subdivisions is proper for me. So at this point, you should have something like this. And now we have just 2 steps left. We're going to reduce the size of the panel, and then we're going to put pipes on the rails, basically. So again, using a similar construct to reparametrize the individual surfaces, we can reparametrize them right here, because that's a set of untrimmed surfaces. So I'm going to take this and copy this whole construction and just plug this isotrim into this isotrim with its reparametrization. Turn this one on, and I'll increase the reduction to 0.05. And there you see, oh, sorry, it should be on both of them now. So we'll do 0.05 there as well, and 0.05 here as well. Okay. Clean that up for you a little bit. Okay, and what we have here is essentially a smaller subdivided surface. Now, is this perfect? No, it's not. Because of the fact that it's a rectilinear form, or a rectangular form, I should say, the actual separation from this edge to that edge is a little bit smaller than the separation from this edge to that edge. If you really wanted to, you could do the math and measure the width of each panel, and then filter in a list of how you want it to be reparametrized proportionally to make it equivalent to inches. However, in most academic applications, that's not necessarily something that's worth your time. In fact, if I look at this and I kind of view it from a distance like this, which is probably fair enough, I won't really know the difference. So this is probably good enough for now. Okay, so that's my subdivided surface, and then I just need to go ahead and pipe. So the next step here is going to be under the surface tab, under the freeform panel, we have pipe. It's right here. And pipe is going to require a curve, a radius as a numerical input, and don't really worry about the E value all that much because we have complete cycles. but it defines how it gets capped at the end. So you could round it off, you can make it a flat cut, or you could just make no cap at the end, and then it's like a straw. But the one that we should be concerned with is the C input, because the C input is asking for a curve, not a surface. So what do we do to break down a surface into its constituent parts to grab the curves? Under the surface tab, again, under the analysis panel, we can do what's called deconstruct BREP. And it breaks it down into its constituent parts, and you've seen this a number of times before already. But which surface are we going to use to pipe? In fact, the glass that we just reduced is going to sit inside of the frame. And so the frame, which is what we're going to pipe, is going to be the outer edge. And so if I kind of go backwards to this subdivided surface, that's the one that I want to break down. So I'll plug that in to deconstruct BREP. Let me turn this off so it doesn't get confusing. In fact, I'll turn this one off as well. And now we have faces, edges, and vertices that we can work with. The good thing is the edges come in packs of 4, so I can just plug in each panel pack of 4 into here, and you'll see that it's gigantic right now. That's okay. What we're going to do is change the radius to be something that's more realistic. In this case, a radius of 0.75, which is going to be a rail of 1.5 inches diameter, which is what we do in the real world in most cases. So we're going to go to, we could do a static number, or we could do a slider, but I'm just going to do a static number of 0.75 and plug that in. Oh, that's right. We're in feet. So with the 0.75, we have to go to math, division, plug that in here. And I could actually just copy this down and make it divided by 12, which would be 0.75 inches, a value of 0.0625. Plug that into R. So 0.0625 feet gives us this rail. And so I'm kind of realizing that my glass technically could get a little bit closer if I wanted to. If I really wanted to calibrate it, I could click here and say 0.04 instead and see if I can get a little closer. That's probably appropriate. I can turn off my old surface here. And so the cool thing here is that now, because I put my rotator where I put it, now that I have two different sets of geometry, I have all these pipes and I have all these surfaces, I can go back to my rotator and I can just rotate the whole thing. So 0 degrees, that's fully upright, 15 degrees tilted outwards. So I'll put it back to a more moderate tilt. And then the interesting thing that I'm going to do next is just create a handrail, because once you kind of tilt it forward, your handrail will have to extend a little bit outward from the guardrail. I mean, it does anyway. You have a handrail that sits 1.5 inches off of the guardrail in most cases. But in this case, we're going to have it tilting forward and then reaching outwards to create the handrail. So going back from our overall full definition, we need to find the spot that we can create a handrail that's going to be exactly vertical from my bottom rail. So it's going to sit kind of 36 inches. Yeah, 36 inches above the ground along the edge here. And so to do that, I'm actually going to use the curve that I offset. Let's see here. There we go, 6 inches. Move curve. Okay, so we can basically offset another curve, except this time we're going to use move, and we're going to use the vectors, except we're going to have to do it on the side. So I'll pull this one above. Let's see, we'll go grab that, this, and this. I'll pull this one above the curve so that we kind of have two offshoots here. So we got one move and another move. Turn these on so you can see them again. Those are the originals. This is my new set, except I'm going to get rid of one connection and change the value to 36 inches. So now I've got a pipe center line that's going to sit 36 inches above the ground, directly above the bottom rail. And the pipe for this one is really as simple as, if it's going to be the same diameter, you actually can just plug it in directly to this pipe, and that's going to work just fine. Otherwise, if you really didn't want to keep the same pipe output, maybe you wanted to make it a different material, you can just copy it up and then override the connection right here, and you've got a secondary pipe. And that will rotate, or will stay static as this rotates. So if you put this up to 0, you're actually going to have a conflict, because the rail is exactly coincident, and that wouldn't actually be accurate. So once you tilt it out, then you've got a handrail that's a little more accurate. So at this stage, we're pretty much ready to move into our applied exercise. And so I'm going to kind of give you a lot of hints, quite a few hints here actually, and I'm going to walk you through the step-by-step process on another file. And so that one would be this one right here. And it's okay that you see this. This is kind of the general shape of the definition that you're going to create. It's part of it. In fact, it's half of it. Actually, in reality, it's more like 90% of it, because the other part is finishing it up. And so let me kind of zoom in real fast on what it means to get to the end. So what you're going to create is what you see on the left. What you see on the left is a pedestrian bridge, much like you just created. It has a handrail. It has guardrails that follow the same kind of sequence that you just saw in the video. However, it's a little bit different. It is built on a curve. It also rotates outward and tilts outward toward the edge. But your job is to make sure that it works on an odd or oblique axis. And so everything needs to be parametric per the original rail. Okay, so this is the only element that you need to model in Rhino. So I'm going to zoom out again real fast, and I'm going to turn everything off so you can start from the beginning. Okay, this is what I created in Rhino. It's just a curve. It actually started off at the origin right here. It's 50 feet long, and I just kind of yanked the center point up a little bit, probably about 20 feet or so, in order to give it a smooth curvature. From there, your next step was to generate a surface on that curve. From generating the surface, your next step was to, or is to, find the surface normal. And then your next step from there is going to be to, well, this is sort of an offshoot. I'll get to that part in a moment. Well, yeah, you should probably do this first. Is to create an extrusion to make sure that it works. And the reason that I tilt it is because when you rotate the thing, you need to make sure that it's actually extruding perpendicular to the surface itself, not along the global axis. So be sure that that is happening for you. Now, I don't want to show you any of the commands here. So moving kind of back to the beginning connections here, you're going to kind of move up here into these next steps. Okay, so that was step 1, to find the normal. Step 2 is to extrude the surface of the bridge itself. Now step 3 is going to be to create your top and bottom rail in order to generate your guardrail. And on a similar note, kind of as a side objective, let's see, turn this on, you're also going to create your handrail curve. Okay, so you've got your extruded surface, you have your guardrail curves, and you have your handrail curve. And then from there, your next step is going to be to tilt it. So let me turn all of these off so you can see. Whoop, you probably want to hold on to this. There you go. So create one that tilts outward a couple of degrees. And then from there, subdivide it so that you can see a number of individual panels. Try to get them to be approximately 4 feet long, but it's okay if they're a little bit longer or shorter. Ooh, well, we might leave that on. And then from there, you're going to reparameterize each of the individual panels. And then at the very, very end, you're going to pipe the handrail. And you're going to pipe the actual guardrail. So what is the real challenge? I pretty much showed you everything that you have to do. The challenge now is going to be follow the instructions that you see on screen here. And you're going to remap this definition again to apply to both sides of the bridge at the same time. So if one side tilts outward at 5 degrees, then the other side should as well. Make sure that it's fully parametric and you only have one slider that controls both of them. I gave you a hint here with the deconstruct brep. This is how you're going to kind of lead away from the actual definitions themselves. So right now you do not see any of the nodes, but you see their shape, okay? And that kind of tells you a lot. It tells you a lot about what you're going to need, what the relationships are for the major elements. You can kind of follow step by step in my video to see the end point of what each one of these actually is, and that should help you work backwards from each point. What I am providing to you is a document that has all of the tools in this definition packaged into some groups that make some sense. It won't be exactly what you see here because each of these individual groups has only 2 or 3 items in it in some cases. And that would be too easy. So your task is going to be to take the information that you see in the file to develop the bridge. Now, I'm giving you everything that you see here, which is everything that you're going to need in order to get it done. You are not limited to using only that. Your task will be to basically create this definition by any means that you can find within the software. So you'll have the next hour of class in order to complete that. I'll be available for questions if you have any. Please follow the instructions that you receive in class or on Tuesday before this class.